start lesson 4 again. So, all right, so we are talking about confidence intervals again. If you're here Thursday, you got a little insight on this. If you weren't here Thursday, hopefully this is helpful for everyone. So we'll just kind of, if you haven't been here before, we basically are just going to go through a quick review of this week's different topics. And then we will go ahead and continue on to do some review questions. And like I said, we'll have an open Q&A at the end. So, okay. So I just wanted to review first samples versus populations. So basically the whole, because this is important to keep in mind when you are talking about different types of when we're making conclusions at the end and also where we're getting this information from. It's important to understand where what a population is and what a sample is, and then kind of why this is happening, and why we're coming to these conclusions, where we're getting them from. So it's important to understand these symbols here that I listed. This is when you see these, you should be able to recognize that X bar is part of a sample statistic, U over there, and that's a mean, a population parameter. It's important to recognize those and make sure that you are able to see them and immediately know that's a statistic, because it's not always going to say this is a sample. You just have to know that X bar means sample statistics. So so yeah, just kind of understand those. I won't go through them one by one, but you can see that on there. Okay, so sampling distributions basically is, all it is when you take all your samples, it's the display of them. That's going to be how we distribute them, what it looks like on a curve. So it's literally just like a visual display of all your samples. And all it's saying here is that we have a mean and a standard deviation. So our mean is always the center, and then remember, standard deviation is the spread. It's just how far out you go on that. And we also call it the standard error. That's something to keep in mind. If you see standard error, just know it's synonymous with standard deviation. So yeah, okay, so going a little bit more in depth to the standard deviation, we do have, so the standard error is our standard deviation of a sampling distribution. So remember, categorical variables are correlated with proportions. So if our equation or our situation is talking about a categorical variable, then we know it's going to be proportions. Or if you see a proportion, you know that we're talking about a categorical variable. And then same thing with means. If we're dealing with means, that means that we're talking about quantitative variables and vice versa. So definitely keep that in mind. Remember, proportions are always between 0 and 1. So that's something that can kind of give away if we're talking about proportion or mean. Means are going to be larger numbers usually. If it's not a small decimal between 0 and 1, check to see if it makes sense that it would be a mean. But if you see a larger number than 1, then you can automatically know that it's a mean and not a proportion. And also our standard error does have an inverse relationship with sample size. So if we, just to visualize that in a way, if we increase our sample size, which we usually denote that as n, then our standard error is going to go down. And then the other way, if we decrease our sample size, our standard error is going to go up. I know some people haven't heard the term inverse relationship before. All that's saying is that when one goes one way, the other one goes the opposite way. They're inverse of each other. So that's just something to keep in mind, and is the notation we use for sample size. And keep in mind that we always want a large sample size. It's the best thing we can do, because if we have a large sample size, it's going to be more representative of our population. So, and our standard error is saying how much error we have. So obviously we want less error. So as you can see, if we have a larger sample size, we'll have less error, which is A+. So let's clear this drawing and do things like this. Okay. Alrighty. So now actually getting into confidence intervals after we have that kind of basis. I always just want to make sure, because you have to know the basis of these things, understand the previous chapters in order to move on. If you don't understand that, it's going to be tough to move on to the next lessons, because you don't have those bases, and then it won't it won't really make sense as to like what we're doing in the next chapter. So make sure you have those basics. That's why you'll see a lot that I always like to review, like the past chapter at the beginning of my reviews, because I think that's very helpful. Hopefully you guys think it's helpful too. We have our confidence intervals, which are basically a range. That's just the definition of a range computed using sample statistics to estimate an unknown population parameter. So a confidence interval is used taking samples. And this is basically the point that we don't have the population parameter, but we do have a bunch of samples that we can take. So in that case, we're going to take all these samples and then go ahead, and then whatever confidence interval we get, we're going to use that as to kind of predict what we think the population parameter is. And yeah, with a given confidence level, that's where like the 95% or whatever comes into play. And then that is, I meant to fix this, I don't like how it's written, but that is how we write like a common equation for confidence interval. This is like our base equation. So we have our point estimate. Okay, actually, I forgot that I can like write up here, which is like, so we have our point estimate, and then plus or minus 2 times our standard error. So keep in mind, the multiplier is not always 2, but it's a common multiplier that we use. You'll see it very often. It's actually technically 1.96, but we often round it to 2. So that's something you'll see very often. As we go forward and use different different levels, different percentages, you will see different multipliers. We'll talk further about where we get that 2 from. So remember, our point estimate is either going to be, ooh, what did I do there? Oh, I don't like how that looks. Boop, 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 boop. Okay. Our point estimate is either going to be p hat, or our other option is the x bar. So these are our point estimate is going to be our sample statistics. So this is why you want to keep in mind these are the symbols we use for sample statistics. Our p hat is our symbol for a proportion sample statistic, and then our x bar is for a mean sample statistic. So that's where we get those from. And so as you can see, these are the middle, so they're going to serve as the center of the confidence interval. So either the mean or the center proportion. So that's our point estimate, and then the plus or minus is how we go left and right to create that interval. So when we do the plus part of the equation, when you do that equation, do the plus part, that's going to give you the right side, and then when you do the minus, you're going to get the left side, and then boom, there's your confidence interval. And it's 95% because our multiplier down here, that's 2. And like I said, not always 2. I just use that as like an example often, just because to keep it consistent. If you have questions about, why I keep saying 2, I mean, I know sometimes that gets confusing, let me know, but yeah, basically that's what it is. So yeah, we will get more into rule of sample proportions and central limit theorem later on, but just as like a preview, that's how we find our standard error. There's just different equations that we use to find that. There's just like different, there are equations to find standard error. There's one for proportions and one for means. Central limit theorem is in regards to means, obviously rule of sample proportions for proportions. So yeah, and once again, sample size has an increased or inverse relationship with confidence interval, like how big it is. So, as our sample size increases, our confidence interval is going to become more narrow. So remember, this makes sense because remember when we increase our sample size, our standard error became smaller. So once again, our standard error, that's also going to make our confidence interval smaller too. So it's the same idea. Once again, always want to have a large sample size, very important. Just leads to better results. So yeah. Okay. All right, cool. So we are going to talk about the empirical rule, which is kind of going to explain where we get this multiplier of 2 from, just to illustrate that. So I kind of highlighted here the different parts of, like, if you're looking at the empirical rule, if you recall, it's talking about the percent of the data that lies in between certain standard deviations. So as you can see that 68% of the data lies in between plus or minus 1 standard deviation. Let me just write that. well, I'll write this next one. So 95, what in the world was that 5? Okay, 95% of the data lies between plus or minus 2 standard deviations of the mean. So all that's saying is that if we were to find the area under this part of the curve between the minus standard 2 deviations and plus all this area in here is going to be 95% of our data. So when we're finding a 95% confidence interval, that's why we use our multiplier of 2, because we're referring to the fact that plus or minus 2 standard deviations, because whatever our mean is, remember this is going to be our point estimate. So whatever our point estimate is, we're multiplying it by how far out we're trying to go. So this is what I was talking about when we do the plus or minus, that's where we're getting these two different, like, lower and upper bound of our confidence interval. And then our standard error, because that's also our spread. Remember, standard error is also our standard deviation of a sampling distribution. Whoa. Okay, yeah, and then remember, this is sample statistics, so that's why sampling distribution. So yeah, that's where this comes into play. This is what I was talking about with the fact you want to make sure that you understand the stuff from previous chapters, understand the empirical rule, because then this equation makes more sense to you, and you're not just plugging and chugging, which isn't always helpful. Okay, so after you, I just splashed on myself. Okay. Okay, so after we interpret the interval, or I mean, after we get this confidence interval, we kind of have to interpret it. We can't just like put these two numbers and be like, we done, this is it. So we want to make sure we're able to interpret it and see what it is. So in this case, and once again, I'm using this 95% confident. It sounds like I'm saying it a lot, but I want to make sure you guys aren't confused. I'm using this 95% as an example. You're going to be able to use different percentages because you can have different levels of confidence, obviously. But for example, if we're doing a 95%, we always talk about, so we are 95% confident that, and so that's always like the beginning part. So this percentage will be whatever your level of confidence is. So it'll be, we are 99% or 95% confident that, and then keep in mind population proportion. We're talking about population. Okay, so remember, I wrote this out before. So we have populations, and then from that we get samples, right? So in this case, keep in mind that, so our population, remember, that's where we get these samples from. And you'll see me write this out all the time. And then from our samples, we make inferences about, I hope you can read that. We make inferences about the population. So the whole point is that we use those samples to make an inference about the population that we don't know. You know, we wouldn't be doing this if we knew the population parameter. The whole point is to try to find out more about the population by taking these representative samples that represent the entire population. So remember, this 95% confidence interval, this came from samples, okay? So since it came from samples, we're making an inference based upon it about the population. So make sure you always say we're 95% confident that the population, and then you just talk about, if you're talking about categorical variables, you'll say proportion. Talking about quantitative, you'll say mean. So it's one of these, it's not both. So either population proportion or population mean in question is between, and then whatever confidence interval you got. So yeah, whatever confidence interval you got is going to be what you're going to use, like that's how you interpret it. Like this first part is the interpretation, and then this is going to be like the actual confidence interval that you got. Yeah, so this is just an example. You know what your calculated interval is your confidence equation. Will be your lower bound and upper bound. So remember, on that curve, that's going to be dependent on what these two numbers were. This will be your lower bound, and this will be your upper bound. Then that's your confidence interval. Whoops. Yeah, something like that. Okay, great. So yeah, I did a lot of writing on that one. Whoa. Alrighty. Okay. Bootstrapping. So basically, bootstrapping is going to be when we're still taking samples, but in this case, we're taking samples and then we're replacing them. So far what we've been talking about is when we're taking these samples and we just keep taking them, and then, when we run out, we run out. But in this case, it's kind of like when we have a smaller sample, and if we did that, we wouldn't be able to get that many samples. So in this case, you take a sample out, put it back in. Take a sample out, put it back in. So yeah, that's basically all it is. And once again, whenever you see something distribution, it's just after you take all of those variables and put them on a visual, that's just your distribution there. So the only difference with this is that when you're still taking samples, but the only difference is that you are going to have you're gonna have replacement with that. So okay, so there's two different bootstrapping methods for a 95% confidence interval. So remember, these are two different methods that you are taking samples and then with replacement. So our standard error method is when your sampling distribution is approximately normal, you can use this one. And this is just a matter of changing the different method on stat key. Percentile, you'll just leave it as what it is, and I'll show you some examples of that. So yeah, percentile method is, you can use that no matter what this shape is, because if you think about it, your percentile method's talking about the percent of data within your curve and within your interval. And no matter what kind of curve you have, it's always going to be 100% under it, so the percentile method can work no matter what. Standard error does have to be approximately normal, because remember, you have that mean, and then your standard is the distribution, so that won't work if you have skewed data. So excuse me. Okay, so here I just have some visuals about what it would look like if you use like the standard error method and the percentile method in this case. So basically what we have here is in stat key, if you were to do the standard error method, we are going to end up here. You can see this is a bootstrap dot plot of a proportion. And I just kind of highlighted here, it's just kind of magnifying what we have in the upper right-hand corner. And so once again, this right here is just our equation, our general equation. Remember, this is our point estimate. So it's a sample proportion plus or minus 2, because we're talking about 95% confidence interval times the standard error. So in this case, we just have our samples, which is our n, and then we have our mean, standard error. And then in this case, all we would do for this is to plug them in if we want to find out our actual confidence interval. So as you can see, this is approximately normally distributed, which is why we can use that standard error method. And this next one is just the same thing except for means. So your point estimate here is your mean, and then you go ahead, actually, SOS, that's not good. This should be X bar. Shame on me. That's X bar. But yeah, so because remember, this is our sample. So yeah, all you would do is plug. So for an example, if we were to do this as an example, I need to choose a different color. So if we were to do this as an example, you would go ahead and do 16.006 plus or minus 2 times our standard error, which is 2.112. And then this is going to give you a lower and then an upper bound on here. So once again, this is our standard error method. Got to make it sure it's approximately normally distributed, which one this one is, which is why we could utilize that. Okay. Awesome. Okay, so this is going to be our percentile method. So remember, we can use this no matter what. This just happens to be normally distributed, but it doesn't have to be. It could be skewed. And the way you do percentile method, the only difference is you just hit two tail. Because all we're showing here, oh, I didn't know you could click on it and it changes. Learn something new every day. Okay, so in this case, the only difference is you're going to be able to, you hit two tail, and that's what's going to give you here a lower and an upper bound. So basically, this like automatically gives you your percentile method or your 95% confidence interval. As you can see here, I don't have an equation over here because you don't have to do it. You just get your lower bound and upper bound automatically. So, And make sure in here you have the percent confidence interval that you're doing, because you want to make sure this is 95% of the data, because that'll be the lower and upper bound that are kind of the end caps of your 95%. Another way to check is to make sure that this outside, the two tails, are making sure that those end up to be 5%. So yeah, that's that. Is it going to work now that okay, here we go. So this is just if you're doing it for proportion, so categorical variables, do the same exact thing. Make sure you hit two tail and 95% in here, and there's your lower and upper bound. So hopefully that's not too complicated. Oh, review questions already. How exciting. All right, we have quite a few. Make sure we understand these. So if you haven't done this before, we just kind of go through these. I'll give you some time to try to answer them, and then we will go ahead and review them at the end. So if you're here on Thursday, feel free to answer these again. Like, it's good practice to always try again. It's totally fine. If you don't want to, that's okay. So yeah, go ahead and try this one. So we have, which statement is true about both P and mu? So go ahead, look through these answers and let me know what you think. Okay, cool. Thanks for participating, Maria. I appreciate it. So yeah, exclamation point B, definitely the correct answer. So this is where I was talking about, you want to make sure you understand the different symbols. So here, let me get my little drawing tool out. So if we go through these one by one, A says P and mu are both statistics. That's completely incorrect because they're not. So boop, boop, boop. That's not correct. C says P is a statistic. That's not even right. But mu is a parameter, so that's true, but the whole thing isn't right. So, and then this last one, this is P is a parameter. That is true, but mu is not a statistic. Sad. So D is incorrect. So B is correct because both P and mu are parameters. Yes. Okay. Looks like, oh, it looks like a little eyelash over here. Okay, cool. Alrighty. So good job. All right, let's do another one. Feel free to participate, everyone. You're more than welcome to join in, you know. Maria always participates. I appreciate that, but you guys are more than welcome to join the train. So, but yeah, all right, let's try this one. So, in a random sample of 100 preschool children, 70% like carrots. That's good. So construct a 95% confidence interval for the proportion of all preschool children who like carrots. So, and a hint here, I just gave you your standard error of p hat, so you don't have to go ahead and calculate that or anything. I don't even know if you guys know how to do that yet, but so here's your standard error. So go ahead, try to calculate this, and then we will go over it. Good job, Maria. No, yeah, so that's definitely the right answer. I didn't ask you to interpret it. If you want, you definitely can. But yeah, so you're right. That is the answer. Let's go ahead and write how we got that. So remember, our general equation is going to be our point estimate plus or minus 2 for a 95% confidence interval times our standard error. So what we could do here, I like to break this apart. So we have our point estimate is going to be, so our random sample, our n is equal to 100, and our point estimate is going to be the 70% because that's the statistic that we got from it. So 0.7 plus or minus 2, and then our standard error, which I gave you down here, is going to be 0.46. And then if you were to solve this, we do get the answer that Maria so graciously solved for us, 0.680, and then 608, sorry, 608, and then, there you go, and then 0.792. Okay, so yeah, and if we were to interpret it, that's a great idea. We should do that, Maria. So we can say we are, Penn State, just kidding, we are 95% confident that the population, and then we're talking about proportions here, proportion, and you can see this is a decimal between 0 and 1, and also we're talking about percent who like carrots, so population proportion of children, preschool children who like carrots is between 0.608 and then 0.792. And if we were to actually, put this into percentages, this is just going to be 60.8% to 79.2%. So yeah, good. Does that make sense to everybody how I did that? Cool. Okay. Is anyone alive? No. Okay. All right. Good. Once again, stop me at any point if you're confused. I don't want to go on if you guys are a little don't understand. So, alrighty. Let me. How is this? Okay. Alrighty. So, let's do another one. Okay, so which of the following is true about the population mean and sample mean? So go ahead, read through these, let me know what you think, and we'll go over it then. Yes, great job. Be confident in your answer. Yes, it's definitely D. So let's go ahead and go through this. So remember, our samples are what we take from our population. Our population is fixed. And our samples are variable because they should be random samples that we take out. I was like going all over the place there. So let's go through this. So A says values of the population mean will vary from sample to sample. That's already wrong. Population does not vary. So remember, our population is fixed, and then our samples are going to vary. So yeah, A is not correct. Values of both the population mean and the sample mean will vary. Population will not vary. So B is not correct. C, valuation. It is okay. Words. Values of the population mean will vary. Like, no, incorrect. It will not vary. Bop. Values of the sample mean will vary. Doop. Yes. And then according to the sampling distribution and the sampling mean. This could also go on to say that the population does not vary. That is also true. So yeah, so D is our answer. Does that make sense to everybody? Yay! All right, awesome. Alrighty, what is next? Okay, this one's a quick one. So we have a data set from a sample of 10, sat 200 students, you and 9 of your classmates. If we were to take a bootstrap sample, is it possible that you could be selected more than once? 2 yeses from Tammy. Confidence. I like it. Yes, Maria. Awesome. So you guys are definitely correct. Yay. Thank you. Perfect. Thank you, Jenny. So that's definitely correct. Because remember, bootstrapping, if you do bootstrapping, you are able to, you do it with replacement. You're welcome, Megan. Yeah, definitely. Have a great night. So yeah, you are definitely going to be able to do this just because if you do have a if you do take a bootstrap, you replace it. So if you were to be chosen and then you get replaced back into the sample, you could be picked out again. So good job. Alrighty. True or false? If a bootstrap distribution is approximately normal, the empirical rule can be applied to construct a 95% confidence interval by multiplying the standard error by 2 to get the margin of error. So yes, Maria, you're definitely right. This is true. This is basically the definition for the standard error method of bootstrapping. So yeah, this is definitely true. I don't have much to say about this one, so all right, good. All right, for this one, it looks like a lot of words, but it's not that bad. So I constructed a bootstrap sampling distribution here for the mean Atlanta commute time. So we had a total of 5,000 bootstrap samples drawn from the available sample of n equals 500 commute time. So this bootstrap distribution has a mean of 29.099 and a standard error of 0.930. So using the standard error method that we've been talking about, what is the 95% confidence interval for the population proportions? Go ahead and try this one out and let me know what you get. Yay, absolutely. You guys did a great job with this one. So let's review how we got this. So remember, our standard error method does use this general point estimate plus or minus. We're talking about 95% confidence interval, so 2 times our standard error. So if I were to go, I'm just going to go down here and do that. So our point estimate here is going to be our, this is from our bootstrap distribution mean of this. So we're going to choose 29.099 plus or minus 2 times our standard error, which they give you of 0.930, which definitely gives you this interval of 27.239 to 30.959. So great, you guys did a great job with that one. Definitely understand that standard error method. So awesome. Alrighty, few more. All right, so we have data from a representative sample of 507 adults who exercise regularly, and they were used to bootstrap a 95% confidence interval of the mean wrist diameter in centimeters in the population of all adults who exercise regularly. Many tab express output I gave you there to the right. So go ahead and interpret this confidence interval. So as a hint, this is when we say we are blah, blah, blah. So go ahead and try this one out. Yes, beautifully said, Maria. I will not read all that out again, but that's absolutely correct. So our mean risk diameter, we are talking about means, which is great. And then in the population, we're making this inference about the population, which is great. And then you definitely put in the variable there for what we're talking about, which is the mean risk diameter, because that is very interesting and important. And then it's between those two, the lower and upper bounds. So awesome. That's a great job. Thank you. And the hashtag we are definitely A+ to that, bonus points. So great job. Alrighty. Let's keep yours. Okay, so then this is just a follow-up question. So do we have evidence that the population mean is different from 11 centimeters or not? So based upon what we just found there. Alrighty, great. So yeah, this is definitely, there is evidence that the population mean is different from 11 centimeters because that is not contained within our interval. So we're saying that we're 95% confident that our population parameter is between 10.469 or 02 and 10.6217. So we're 95% confident that it's in there, but 11 isn't in there. So technically we're only 5% confident that it's over there. So technically we're only 2.5% confident because it's to the right. So so we're definitely not confident that we're in it, so we can say that the population mean is different. So awesome. Alrighty. Okay. Woo. All right. So yeah, go ahead. You're more than welcome to watch these back on my YouTube channel. All the sessions from tonight and before will be on there. We'll have our lesson 5 review on Thursday. If you have any questions, go ahead and type them into the chat box. And if you haven't given me your Penn State ID, go ahead and do that for me. And if not, you guys are good to go and have a great night. See you Thursday.